Welcome all. Now we are going to discuss about Holder's inequality. The statement is for 1 less than p less than infinity, let q satisfies 1 by p plus 1 by q equal to 1. Then summation j running from 1 to n modulus of aj bj is less than or equal to summation j running from 1 to n mod aj raised to p whole raised to 1 by p into summation j running from 1 to n mod bj raised to q whole raised to 1 by q for aj and bj element of k and j equal to 1 to etc. n. Okay, now let's discuss the proof. For proving this inequality, we have to first prove a Young's inequality. The inequality is for a greater than or equal to 0 and b greater than or equal to 0, a into b is less than or equal to a raised to p by p plus b raised to q by q. First we will look at the proof of Young's inequality. If b equal to 0, we can see that 0 is less than or equal to a raised to p by p in the Young's inequality. This is a true statement because a is greater than or equal to 0 and p is in between 1 and infinity. So 0 is less than or equal to a raised to p by p is true. So if b equal to 0, the Young's inequality is true. Now consider if b not equal to 0, then also we have to prove the Young's inequality. If b not equal to 0, then the case is b greater than 0, since b is greater than or equal to 0. Now we are going to consider a function x of t whose domain is closed 0 infinity. Okay, consider the function x of t is equal to 1 by q plus t by p minus t raised to 1 by p where t is greater than or equal to 0. Then if we check the derivative of this function, we can see that x dash of t is equal to 1 by p into 1 minus t raised to minus 1 by q. Okay, now for searching for the critical points, putting x dash of t equal to 0, we will get t equal to 1 is the only critical point. Okay, so at t equal to 1, we have to check whether it is an absolute maximum or an absolute minimum. For that, when t less than 1, what about x dash of t? When t less than 1, we can see that x dash of t is less than 0. That means the function x of t is decreasing when t is less than 1. Okay. Also, when t greater than 1, we can see that x dash of t is greater than 0. That means the function x of t is increasing when t greater than 1. In the right side, I have plotted the domain closed 0 open infinity, and 1 is our critical point, and in the left side we can see that the function is decreasing, and on the right side of 1 we can say that the function is increasing. So at the point t equal to 1, we have an absolute minimum. Okay, that is t equal to 1 is an absolute minimum for the function x of t. By the definition of an absolute minimum, the value of that function at that point is less than or equal to x of t for every t in the domain. That is, x of 1 is less than or equal to x of t for every t greater than or equal to 0. What is x of 1? By putting t equal to 1 in x of t, we can see that x of 1 is equal to 0. So we have 0 less than or equal to x of t for every t greater than or equal to 0. By substituting the function x of t, we can see that t raised to 1 by p is less than or equal to 1 by q plus t by p for every t greater than or equal to 0. This inequality is true for every t greater than or equal to 0. So we are letting t is equal to a raised to p by b raised to q. Here a and b are greater than or equal to 0, and p is also 1 less than p less than infinity. So here t is a positive quantity, and we can without any doubt we can substitute this to the inequality we are obtained. So we get a raised to p by b raised to q whole raised to 1 by p is less than or equal to 1 by q plus a raised to p by b raised to q by p. Okay, that is a by b raised to q by p is less than or equal to 1 by q plus a raised to p by b into p into b raised to q. Now multiplying this throughout by b raised to q, we can see that a into b raised to q by b raised to q by p is less than or equal to b raised to q by q plus a raised to p into b raised to q by p into b raised to q. That is a into b raised to q minus q by p is less than or equal to b raised to q by q plus a raised to p by p. But q minus q by p is nothing but that is equal to 1. We can see that a into b is less than or equal to a raised to p by p plus b raised to q by q. This is our Young's inequality. So we have proved the Young's inequality, that is for a greater than or equal to 0 and b greater than or equal to 0, a into b is less than or equal to a raised to p by p plus b raised to q by q. Now we are going to prove the Holder's inequality. For that we are just substituting alpha and beta as the terms in the right side of Holder's inequality. That is alpha is equal to summation j running from 1 to n mod aj raised to p whole raised to 1 by p, and beta is equal to summation j running from 1 to n mod bj raised to q whole raised to 1 by q. Then we can clearly see that alpha raised to p is summation j1 to n mod aj raised to p, and beta raised to q is summation j1 to n mod bj raised to q. So what we have to prove is summation j running from 1 to n mod aj bj is less than or equal to alpha into beta. Okay, this is our Holder's inequality where alpha and beta is defined just above. Okay, so we are going to prove this Holder's inequality. First consider the case alpha equal to 0. That means summation j1 to n mod aj raised to p whole raised to 1 by p is equal to 0. This means that the terms mod aj raised to p is equal to 0 for every j running from 1 to n. That means mod aj equal to 0 for every j, and so the summation 1 to n mod aj bj is equal to 0. Okay. Also alpha equal to 0 implies alpha into beta is also equal to 0. Thus we have summation j1 to n mod aj bj is equal to alpha beta if alpha is equal to 0. Similarly, we can see that if beta equal to 0, this is the same case. So Holder's inequality is true either alpha equal to 0 or beta equal to 0. Okay, now consider the case alpha and beta are greater than 0. Then also we have to prove the Holder's inequality. So now we are going to apply the Young's inequality. Like consider in the Young's inequality, let a is equal to mod aj by alpha and b is equal to mod bj by beta for j equal to 1 to x n. Okay, apply for each j a and b as mod aj by alpha and mod bj by beta in the Young's inequality. We can obtain mod aj by alpha into mod bj by beta is less than or equal to mod aj raised to p by alpha raised to p into p plus mod bj raised to q by beta raised to q into q for j equal to 1 to x n. Okay, that is modulus of aj bj is less than or equal to alpha beta into mod aj raised to p by p into alpha raised to p plus mod bj raised to q by q into beta raised to q for j equal to 1 to extra n. Summing up all these inequalities, we can see that the left side becomes summation j1 to n mod aj bj, and that is less than or equal to alpha beta into summation j1 to n mod aj raised to p by p into alpha raised to p plus summation j1 to n mod bj raised to q by q into beta raised to q. This is equal to alpha beta into taking outside the constants, that is 1 by p into alpha raised to p into summation j1 to n mod aj raised to p plus 1 by q into beta raised to q into summation j1 to n mod bj raised to q. And the summation j1 to n mod aj raised to p is nothing but alpha raised to p, and summation j1 to n mod bj raised to q is nothing but beta raised to q. And substituting this, we can see that this is equal to alpha beta into 1 by p plus 1 by q, that is alpha beta, since 1 by p plus 1 by q is equal to 1. Okay, thus we obtained summation j1 to n mod aj bj is less than or equal to alpha beta as we decide. That is summation j1 to n mod aj bj is less than or equal to summation j1 to n mod aj raised to p whole raised to 1 by p into summation j1 to n mod bj raised to q whole raised to 1 by q, where 1 less than p less than infinity and 1 by p plus 1 by q is equal to 1. This is the Holder's inequality. Now we are going to discuss about the Minkowski's inequality. The statement is, for 1 less than or equal to p less than infinity, we have summation j1 to n mod aj plus bj raised to p whole raised to 1 by p is less than or equal to summation j1 to n mod aj raised to p whole raised to 1 by p plus summation j equal to 1 to n mod bj raised to p whole raised to 1 by p. Okay, we are going to see the proof as two cases. The first case is p equal to 1 and the second case is p greater than 1, that is 1 less than p less than infinity. Okay, if p equal to 1, the result is very clear, because we know that the triangle inequality, that is modulus of aj plus bj is less than or equal to mod aj plus mod bj for every j equal to 1 to n, and adding up we can see that summation j1 to n mod aj plus bj less than or equal to summation j1 to n mod aj plus summation j1 to n mod bj, which is the Minkowski's inequality when we substitute p equal to 1. So the inequality is true when p equal to 1. Now we assume the case 1 less than p less than infinity. Okay, remember in this case, that is 1 less than p less than infinity, Holder's inequality, we can apply Holder's inequality. Okay, so now consider summation j1 to n mod aj plus mod bj raised to p. This can be written as summation j equal to 1 to n mod aj plus mod bj into mod aj plus mod bj power p minus 1, right? Then we are splitting this summation into two terms, like summation j equal to 1 to n mod aj into mod aj plus mod bj raised to p minus 1 plus summation j1 to n mod bj into mod aj plus mod bj raised to p minus 1. Now we are applying Holder's inequality in each of the summations. So we get this is less than or equal to summation j1 to n mod aj raised to p whole raised to 1 by p into summation mod aj plus mod bj raised to p minus 1 raised to q whole raised to 1 by q. Okay, plus, and applying Holder's inequality in the next summation, we can see that summation j equal to 1 to n mod bj raised to p whole raised to 1 by p into summation j equal to 1 to n mod aj plus mod bj raised to p minus 1 raised to q whole raised to 1 by q. Okay, and taking outside the common term, this is equal to summation j1 to n mod aj raised to p whole raised to 1 by p plus summation j1 to n mod bj raised to p whole raised to 1 by p into summation j equal to 1 to n mod aj plus mod bj raised to p whole raised to 1 by q, because p minus 1 into q is equal to p. Okay, the reason is 1 by p plus 1 by q is equal to 1, that is pq is equal to p plus q, and so p minus 1 into q is equal to p. Okay, and we can see that in the left side we have summation j1 to n mod aj plus bj mod aj plus mod bj raised to p, and in the right side also we have a term like summation j equal to 1 mod aj plus mod bj raised to p whole raised to 1 by q. So we are considering that term to the left side, we can see that the power becomes 1 minus 1 by q. That is summation j1 to n mod aj plus mod bj raised to p whole power 1 minus 1 by q is less than or equal to summation j1 to n mod aj raised to p whole raised to 1 by p plus summation j1 to n mod bj raised to p whole raised to 1 by p. Okay, and in the left side the power becomes 1 by p, since 1 by q plus 1 by p is equal to 1, and we can see that summation j1 to n mod aj plus mod bj raised to p whole raised to 1 by p is less than or equal to the right side. Let it be equation number 1. Also we know that the triangle inequality mod aj plus bj is less than or equal to mod aj plus mod bj for every j equal to 1 to n, and adding up we can see that summation j1 to n mod aj plus bj raised to p whole raised to 1 by p is less than or equal to summation j1 to n mod aj plus mod bj raised to p whole power 1 by p. Let it be equation number 2. Combining these two inequalities 1 and 2, we can see that summation j1 to n mod aj plus bj raised to p whole power 1 by p is less than or equal to summation j1 to n mod aj raised to p whole raised to 1 by p plus summation j equal to 1 to n mod bj raised to p whole power 1 by p. This is the Minkowski's inequality. Thank you.